Hello everyone, good evening. I hope I'm properly audible. Myself Shitesh, I'm the web administrator in the house and I welcome you all to this revision session for your subject of PDSA, the Data Sciences and Algorithms course on diploma level. So without delaying further, I'd like to introduce you to your instructor for this session. It's Saransh Sini. Saransh, I hope I'm audible to you.
Yes, Satish, you're audible.
Okay, thanks a lot for agreeing and taking this session. Without a further delay, I would like to forward it to you so you can continue.
Okay, guys, so I'll start sharing my screen. Second. Yeah. Okay, so first of all, I'll start with a basic introduction. So, hey guys, I'm Saraj, and I am going to take this session for PDSA, and I was an XPA of PDS, and in this session, we'll be looking at weeks from 5 to 8 because though the syllabus is from 1 to 8, but we'll be looking at weeks from 5 to 8 because 1 to 4 were already covered in the previous revision session. That was one. Hello. So, wait, is my voice clear?
Yes, Saransh, it's clear.
Okay, okay, okay. So, so let's get started with this session. I request your uh, due interaction with me during the entire session. I encourage you all to ask questions. I won't suggest you to just raise up your hand and ask questions. I would suggest you to just go ahead and ask those questions, whatever you have in your mind. Because while I will be busy on the screen, jotting down each and everything and explaining you stuff, I won't have the leverage of looking at the Google Meet screen again and again. So just open up your mics and ask for questions. And I seriously recommend you guys to just ask whatever doubts you have. It can be uh, anything that you have problems with. Can be something silly. It can be really remarkable as well. So that's never a case. Just ask those questions. A it's not a PE session or an instruction session where you will have some hesitations to show. Simply go ahead and ask for questions. Okay. All right, guys. So let's get started with this.
Hey Saransh,
Kush.
can you zoom a little bit your screen?
Yeah, sure. Uh, Wait a sec. Okay. Actually, the thing is that I will be jotting down at this uh, at this scale. So the questions I just reduce the size and dimensions because I had to fit them on the screen. So don't worry about it. I will be zooming in time after time after whenever we are solving these questions. So I hope that's fine with you. Okay. So the strategy that we're going to take for this session is that we will be solving few questions along with discussing the topic. So Uh, for example, we have the exercise algorithm first, and we have Prim's algorithm. So we will be looking at the questions. Firstly, I will be giving a brief introduction and a brief explanation about the topic, and afterwards we will be solving the question. Okay. So that's the approach that we're going to take. Anyway, let's get started. Okay. So from week 5 to week 8, we have a bunch of stuff, and I would say it's a considerable amount of stuff that we have on our hands. So in week 5, we have stuff like Dijkstra's algorithm. We have like spanning trees in question, spanning trees, okay, and how you are going to traverse those spanning trees. Rice algorithm, Prim's algorithm, Kruskal's algorithm. Bellman Ford, Floyd Washer algorithms. That all we have in the week 5. In week 6, I believe that we are introduced to heaps and how heaps are, how to get along with heaps. the functions, what all you can perform on them, heap sorting and all. Uh, so week 6 is heaps, heaps. Week 7 is going to be uh, PST, binary search trees and AVL trees, and week 8 is divide and conquer. Okay, so we will be discussing only these 4 weeks in this current session, obviously because of time constraints. Uh, if you wish to study one, week 1 to week 4, then on the Kaziranga House YouTube page, you can find my session which I took in during the time of this one as well. So you can have a quick revision with that. Okay. Without further ado, let's get started with all these. And again, I recommend you guys to just hop on the mic and ask your questions whenever there is a no. Okay. So let's get started with Dijkstra's algorithm. Okay. So Dijkstra's algorithm is one of those algorithms which helps you which helps you find the shortest path from one single point to other points. So what do we mean by that? For example, just give me a second. Okay. Dijkstra's algorithm is one of those in which you will be asked to find the distance of point. Let's take one of these. Let's take point A to uh, all others. Okay, I need to find the shortest distance. Okay, so the basic functionality of how you're going to perform this algorithm is pretty simple, and we'll be looking at how it's going to take place. Okay, okay. So first of all, let's try to solve this question, and along with solving this question, we'll be looking at the algorithm as well. Okay. So first of all, you have to maintain whenever you're solving that's your algorithm. Uh, you have to maintain a list of what all are closest to you. C, D, E, F, G, H. Do we have H? No, we are stopping at G. So uh, at the very beginning, we'll be taking the distances from of all these points as infinity. So infinity is just a method of it's just a placeholder. Okay. So what do we mean by infinity? It's just that yeah, uh, from point A we have infinite distance to, let's say, point B, point C, point D, point E, and point F. Okay. Now going ahead, we will be actually running this algorithm and finding out the shortest one. Okay. And in the question itself, we are being asked that Dijkstra algorithm is used when vertex A as the source vertex. What are the shortest distance from vertex A to all vertices? Okay, that's what we have to find. Now, this is vertex A at hand. This is vertex A. So we have to find the shortest distance. And first of all, let's get started with it. So going So we can see that vertex A is going towards it has a path to vertex B, right? And we can see that okay, so the path from vertex A to vertex B, we have written overhead two, right? Two is let's say the distance between these 2 points. Okay. Now what we'll do is, and what is going to be the general thing that we have to do in the ISO algorithm is that we have to whenever so let me just jot down the rules of this. Whenever uh, the rules are the rules are that if the current distance is more than the distance we found, substitute it. Okay. So what do we mean by that? So we can see that from point A. So okay. So point from point A to point A, it's obviously going to be zero distance. If then from point A to point B, we have found that okay, so distance is two. So we can safely replace this infinity with two. Okay, because infinity is much bigger than two, right? So we can replace it safely. Next, what we're going to see is okay, so we are currently at okay, so also A is going to D as well. So we can safely replace infinity with one. Then we see that B now let's come to B now. This is a B. From B, we can see that okay, D can be okay. So now at B, we know that the distance from B is two, right? So whenever we see okay, so D is going to D, all right. B is also going to E. Fine. Now, what you have to do is, whenever you have this kind of situation, we know. Okay, someone tell me what should I replace E infinity with? Any one of you just open up your mic and speak up.
3.
12.
So we should replace
3.
infinity with three. Okay, why do you think that that's the case?
A to D, then D to E. It's
Yeah,
total
that's
3.
weightage.
That's the
Wait,
minimum.
wait. Please. Oh, okay. That way. Okay.
Yeah,
So
that's a short.
okay. So in this situation, we have two options. Firstly, is that we can either go from two, we can go from B, and then we can go to E. In that case, we'll have two options. We'll have either 12 or 3, right? Either we can take this way or we can take this way, right? And we are going to take the minimum. So E's infinity is going to be replaced by 3. And you know what? You can pretty quickly do all these calculations. Uh, like, okay, this is done. Then what we're going to do is, do we have an access to other nodes as well? Uh, okay, so B is going to remain the same at 2. Is same at 2. 3 has a value of, E has a value of 3. Perfect. And D has a value of 1. Let's check about other nodes as well. So D is going towards C. The the distance from A to C, it's going to be 1, 1, because we are going from this to this now. So it's going to be 1 plus 2, which is 3. And then we have to say, okay, so is there any, can we reach F? Okay, so A to D, and then D goes to F, which makes F 9, because we already had a 1 on it, right?
F
We
is
had a 1
6.
on it. Huh?
F is 6.
FS6.
A to
Okay,
D,
so that
then G, then F.
okay, A to D, then G, and F. Perfect. So that's another pathway that we can explore. So we can see that we have two options again over here as well. So first is from A to D to F, which is 9, and the other option is A to D to G to F, which is 1 plus 4 plus 1, which becomes 6. Perfect. Whoever is asking, whoever is answering, you are doing a pretty good job. Perfect. Okay. Uh, can
I
we
have a doubt.
see another pathway that's going to F? Yeah, we have another pathway that's going to F, which is 1 plus 2 plus 5, which becomes 8. And again, this is just another option that we have at hand. Okay, so obviously we're going to select the least one. Next comes G. Uh, we have how many different options that we can have? We are going to have again two options, and these two options are going to be we can either come from A to D to G, which is 5, or we can go from A to D to E to G. Okay, this is one pathway, this is one pathway, this is another pathway, and this is another pathway. And we are going to find 1 plus 2 plus 3, this is 9, and this becomes 5. Okay, so we have a 9, and we are going to have 22. So we're going to select 5. So these are your answers. So you can pretty confidently select anyone, the correct option. So it's
I have a
0,
doubt.
2, 3, 1, 3. We have 3, yeah, 6,
Yeah.
and B. I guess that second option is correct one. Can you guys give a confirmation on this?
Yeah,
Yes.
option B.
Option B, no? Okay, perfect. Okay, so do you guys have any doubts in Dijkstra's algorithm and how we are going to traverse
Yes.
through?
Am I audible?
Yeah, you're audible.
Yeah. Can you please zoom in once?
Sure.
Let's say D to G, there is no connection. There is no edge.
Mhm.
If the
Yeah.
if the both the part contains equal weightage, which part it will choose?
If both of them are going to contain equal weightage, means if this is not in the dictionary,
Yeah,
then
D to F.
which all pathways do we have? So it's A to D to E to G and A to B to
No,
E to
no, I'm asking for F.
or F you're asking. Okay. So in this case, yeah. So in this case, if that's the case, well, that doesn't matter now. We just have to find the least amount of distance, the shorter distance, right? From A to D to F, it's going to give you 9. From A to C to F, it's going to give you 9.
So which path it will choose? Algorithm.
Uh, well,
We
algorithm
will
can
choose
go,
this, 8 ADCF.
okay, why do you think that's the case?
From A to D, then C, then F, it's 8. That's the
Yeah,
Yeah.
that's
shortest.
it. No, no, but A to D to F, he's asking that 8 from A to D to F and from A to C to F, that's the same distance, right? 9.
We can't go from A to C now.
Oh, yeah. Yeah, yeah, yeah,
Yeah.
yeah. Yeah, that's good. That's good. We can't go from A to C because that's this edge.
Unidirectional. Okay.
Right. So that won't be the case. But anyway, if this arrow was inverted, if this arrow was inverted, and you would have had a situation like this, in that case, I think that uh, generally it's mentioned in the question that if that's the case, you have to take the alphabetically you have to take the edges in the alphabetical order. So that would be A to C to F.
Okay. Thanks.
It's generally mentioned in the question. Okay. Okay. Anyways, let's move ahead and talk about. Hmm, wait, wait, question. Okay. Let's go ahead and see it. Okay. So I'm going to just leave the Dijkstra algorithm, Prince algorithm for the moment, and we'll be looking at other stuffs, which includes heaps, binary search trees, AVL trees, and all that. Okay. So uh, let's hop on to heaps and what do we understand by heaps? Okay. Just give me a second. Okay. So what do we understand by heaps? Basically, heaps are heaps are stored in like they are derived from the concept of priority queues, but we won't be going into that at the moment. It's basically an array of it's a kind of data structure. Okay, it's a data structure where you can represent an array. For example, this is an array. Uh, Okay, this is the array 8, 1, 4, 5, 2, 10. This is how you are going to fill the heap. Okay, again, I'm going to reiterate on how we are going to fill the heap. So it's basically you're going to take the first element, which is 8. Then you're going to create two children out of it, which is, and then you're just going to continue iterating over the array. That's how you want to create a basic heap. Okay, it's just simple. Like you just have to keep on inserting these elements. Now we have three different kind of heaps. Okay, one of these kinds is a min heap, and then there is a max heap. Okay, there is a min heap and there is a max heap. Now, what do we understand by min heap and max heap? Okay, I should have drawn it. Something else. Okay, what do we understand by min heap and max heap? So basically, in a min heap, the so let me just jot down the rules first. The rule is that the parent should be less than the children, and in the max heap, the parent should be greater than the I'll just write kids. Okay, that's the kids. Let me give you an example of a heap, and you guys are going to tell me which kind of heap it is. Okay. Let me take the example.
Exit.
Okay. Which kind of heap it is?
Maxi.
Perfect. It's a max heap because if you look at it, that looking at this, we have 71, 46, 27. So the parent is always greater than the children. Okay. In fact, in this case, at every parent-child conjunction, we can see that the parent is greater than the child. Right. Whereas if you're going to write down this heap as an array, it's going to be something like this. 71, 46, because remember that heaps are basically just, we are just iterating over the array. It's going to be 37, 29, 1, 5, 8, 32. Okay. So this is the array representation of this heap. And at first look, you might think, okay, so this should not be this might not be any kind of heap. Like it doesn't show any, like in a first impression. If one takes at it, they might think that, okay, so maybe this is not a max heap or a min heap. It's just a basic heap. But that's not the case. You just have to arrange these numbers in a heap format. And then you will see if it's a max heap or a min heap. So just remember in examination, don't jump to the conclusion. Just draw the heap once and you'll get the answer. If it's a max heap or a min heap or just an ordinary heap. Okay. So let me see. Okay, so we'll be looking at some operations that you're going to perform on heaps. So first operation, let's perform on this heap itself. First operation, it's going to be inserting an element. Okay, we have to insert an element, and inserting an element, it's okay, inserting an element. So let's say I want to insert 37. Okay, not 37. Let's take 31. Okay. Where do you think that I should insert 37?
At
Anyone?
29.
Hmm.
At 29.
At 29. Okay, perfect. Because that's the next place where a heap is going to be created, right? So at 29 is the vacant space that we can fill. It was, I guess, 27 anyway. So this is where I'm going to insert it. Okay. But is this following the rules of a max heap?
No.
It's not following the rules of a
No.
max heap, right? So what you're going to do is, if you come across this situation where you are inserting an element and it's breaking the rules, you are going to perform something which is very elementary in nature, which is swapping. Simple swapping. Okay. Just swap this element with its parent. Okay. And it's going to look like this 31 and 29. Perfect. Right. Now it's following the rules and we have successfully done it. Okay. Uh, in the same what it's it uh, way, you can keep on inserting it and you can keep on inserting it and actually let's say now we have to insert another point which is what we can do. uh, let's say 7, let's say 60. Let's say we have to now add 60. Now adding 60, it will be added. Let's take a different color. It's going to be added over here. 60, right? Again, it's creating a problem. So just delete the swap the parent with the child. I guess here was 31, right? So here it goes 46, 60, right? I think now it's at the correct place. Correct. So anyone having any doubts or any additions that you might want to do? Anyone?
Yeah, so a heap can be of only two types, either max heap or min heap.
Well, that's in the syllabus. So yeah.
Okay.
Okay. So second. Mhm. Okay. So this is the insertion of an element, and the rule that you're going to follow is, we just clearly write it down. If conflict, swap parent with child. Okay. Now next part of this is deleting the maximum element. Next operation that we can perform on a heap is deleting the max, delete max. And this operation actually involves deleting the maximum element out of the list, out of the heap. Okay. So over here, the maximum element is obviously 71. It's at the very top of the heap, and it makes sense that it's going to be the maximum one. Okay. Now, when you're going to delete it, what's going to be the operations that you're going to perform? Anyone? Can you open up your mic and speak up? What will be the operations?
May I?
Yeah, sure.
Yeah. Yeah, we will delete 71. 60 will go on the top, and 46 will replace 60,
Hmm.
and the left side will remain same, and
Hmm. Okay,
29, 31 will replace 46.
perfect. Okay. Now, uh, wait a second. Okay. So this is one approach that we can try. We can simply remove 71 out of the picture and move the heap upwards. Like we can just move this up, move this up, move this up. This can be done. Right. And this sounds like a practical approach as well. But what we can do else is that, and let's just check if this works or not. I'm not sure myself, but let's just check. We're going to delete the left side, the furthermost element uh in the heap, and it's going to go up over here. Okay. Let's choose another color out of it. Uh, it's 31 over here. Okay, it's going to go up, and now we are going to perform the swaps. Okay, now we should be performing the swaps, and okay, and we are going to choose the maximum elements out of it. Okay, so we can see the children when we're looking at the children of 31, they are 60 and 27, right? We are going to swap them with the maximum one, which is 60, and 60 is going to go up. Again, whoever spoke, this is exactly the same strategy that we are going to perform, but in a bit more organized way, right? So we are going to remove 60 and we're going to swap it. So 60 is going to be here and 31 is over here. Perfect. Now, again, we are going to swap with the largest child, which is 46. 46 is the largest child. So 46 is going to up, 31 is over here, and here we can stop, right? This is exactly what you said, but just like we're just performing it in a much more systematic way. Okay, does anyone have any doubts regarding this? The max and swap with max child. Okay. Anybody having any doubts regarding this? Okay, I think we are out of doubts. Okay, so let's move ahead. Actually, I'm just opening up few things to take a reference from. Okay. Uh, okay. So now let's move on to binary search trees, and which is one of the most interesting topics in this entire course, just binary search trees. Uh, let's move on to this. Uh, I hope that we don't have any doubts regarding heaps and how other operations are performed on heaps, right? So let's move on to binary search trees and let's see what actually is hidden in these this kind of data structures. So BSTs or binary search trees is just another kind of data structure. Okay, and it just like any other data structure is going to have some of its rules. And the rules are that given, let me just draw a tree. I hope that you are aware with the binary search. So just like in binary search, the whenever you are performing binary search, so let's say this is a sorted array. So let's take 7 into account. We can see that the left side of 7 is less than it. It's less than it, and the right side is greater than it. Right. So the same principle is going to perform over here. The thing is that given a binary, so let me just fill in the values as well. Let's make it 7, 5, or let me just redraw it. Going to be 7, 5, 9, 1, 2. Here we can do 8 and 67. Let's just go above the limits. Okay. So this is a valid binary search tree, right? And the rules. Can anybody tell me the rules that the binary search tree follows?
The greater one should be placed on right side, and the lesser one should be placed on left side.
Perfect.
So
So
two,
that's
two should not be on right side of five.
absolutely that's one mistake, and
It should be on right
that
of one.
exactly it should be on the right of. So
One more thing, what is the basic
yeah,
difference between BCT and BST?
BCT. What is
Yes.
BCT? Can you please tell me? Maybe I've forgotten that. BCT.
Mm, wait.
Like, but I just maybe I'm not able to recall what was BCT. Can you please tell me the full form either?
Same, I guess it's something else, not BCT.
Okay, okay. No worries. Yeah.
Okay, no worries.
Whenever
You
you,
can continue.
yeah, yeah. Okay. So, uh, kudos to whoever figured, who pointed this out. So, one should be, so two should be on the right of one. Okay. And the principles that we are going to perform over that BST is going to follow is that the right subtree, the right subtree should contain values greater than the root, and the left subtree should contain values less than the root. Now, let's just forget about the definitions and let's look what we actually mean by these words. So, these words basically mean that this is the root, given that this is the root, and we are considering the entire BST. So, this is the root, and the right subtree is the right subtree. So in a BST, you have right subtree and left subtree. So the right side of a tree of a root node is called a right subtree, and the left side of a root node is called left subtree. Not left subtree. Okay, this is the left subtree. So this right subtree and left subtree. So the rules are that the right subtree should always contain elements which are greater than the root, and the left subtree should always contain elements which are less than the root. That's the two rules that you have to follow for sure. Okay, and these rules do not end over here. They are going to be executed in every level of the PSG. Okay, so by every level, I mean that let's remove this. By every level, I mean that it's going to be executed on this entire BST. It's also be going to execute it on this left subtree as well, because it's a tree as well now. It's going to be executed over here as well, and it's going to be executed over here as well. On every level, it's going to be executed. Okay, so okay, so this is how a binary search tree is going to be uh, represented. Okay, now before going to AVL trees, which is just another form of binary search trees and a bit more advanced form of it, we are going to talk about some operations that you can perform on BST. Okay, so first operation that you can perform on BST, I hope that everything is clear up to this point, right? Anybody having any doubts in BST on how we are actually creating all this? Uh, like any suggestions that you might want to give?
Yeah, I have one small doubt.
Hmm, sure. Please ask us first.
Yeah, that the given tree is not strictly BST, right?
Yeah, it's not strictly BST. Yeah, that's true. Because strictly BST, as the question suggests, that it should contain either it should have zero or two children. It shouldn't have one children. So in a BST, uh, you can either have zero to two children. Zero, either you can have zero, either you can have one, or either you can have two children. But in a binary search tree, in a strictly binary search tree, you're just going to have zero or two children. That's one rule that has been given in this particular question. And at this moment, we are not following this question. I'm just explaining you what's BST, and just giving a brief revision of BST and what all you can perform with that. Okay. So this is the okay. So here we are.
Sir,
So this is
what will
the
be the answer of the question?
answer of the question. The tree is said to be okay. If binary search is strictly binary tree, okay, and have
Please
four
repeat
leaves,
it.
what is the total number of nodes in the BST? Okay, so just draw this out. So it's strictly binary search tree now. So one, two, three, and what it said that has four leaves. Okay, so here is the answer. It's we can see that just construct the binary search tree without any node having one child. Either it should have zero or one two children. So in this level, we can see that we have four leaves, one, two, three, and four, and then just count the number of nodes. So it's seven.
Okay, sir.
Yeah. Okay. So moving ahead, and let's head on to how you're going to perform some operations on BST, and I'll be going one by one on performing these operations. So first of all, we'll be talking about the ordered traversals. Ordered traversals. Okay. Now, what do we understand by ordered traversals? Let me just give you an example. Uh, yeah. Mm, Okay. The example is over here. Given this tree, okay, so first of all, let me just tell you what are ordered traversals. So we have three types of ordered traversals, which are in order, pre-order, post-order. Okay, so this is the these are the three traversal mechanisms or techniques that we have. And let me just draw a binary search tree, or let's just take this particular binary search tree. What's the harm in taking this one? Okay, let me just redraw this binary search tree. It's seven, seven, five. Let's make it 17 and 15. And here we have 10. Over here we have 16. Uh, here we have 12. Here we have 6. And here we are going to have 1. Next, it's going to be 18. Go for it. And let's have 90. Because why not? And here we have, uh, let's not take, okay, let's see what's the harm. Here we are going to have, okay, so let's have 17.5. Okay. Or just for the sake of simplicity, let's not have it. Let's take 71. And here we are going to have 5,500. Okay, this is the binary search tree that we have at. So just everyone just go through it and check if I have made some error. And is this eligible to be called a binary search tree? Anyone?
No error, sir.
Oh, so let's talk about in order traversals. Traversal. And what do we understand by in-order traversal? It's a basic. So okay. So can anyone tell me what does traversal mean? Like, What's the basic meaning of traversal?
Iteration, iterating through
Exactly.
each
It's
and
just, you
every.
know, yeah, it's going over each and every element of the binary search tree or just
Mm,
roaming around the binary search tree. Okay, that's one way of understanding it. So, uh, we are going to go over each and every element of binary search tree, and there are multiple methods. There are three methods of that traversal, and we are going to look at one of each one. So first of all, it's in order traversal, and the way that we are going to follow is that firstly you're going to go towards the uh, I hope that I'm correct. Okay. So firstly you're going to towards the left subtree, left subtree, then you will go towards the root, and then you're going towards the right subtree. Okay. This is the order that you have to follow. Now, what does that mean given this binary search tree, given this binary search tree? You have to go towards the left subtree. Okay. So the left subtree of this binary search tree is this. Okay. Now, again, you have to perform the same operation. You have to go towards the left subtree. Okay, because left subtree is going to be it's coming first in the order traversal. No? So just go towards the left subtree again, left subtree, then we have left subtree again. Okay, and here we are at an end at the end of a leaf. Okay, so given this, it's going to be the left subtree. So first of all, you're going to perform operations over here. So we're going to take left subtree, which is 1. Okay, then it says a root that we have to take a root, which is 6. Then it says you have to take right subtree. So in this particular tree, we don't have a right subtree, right? So just leave it. Okay. Okay. Now going ahead, what should be the next numbers? Can anybody tell me what should be the next numbers in this or in order traverse?
10 and then 12.
Perfect. So 10 and then 12 because after considering this left subtree, we are going towards the root and then towards the right subtree. Right? Perfect. Okay, one more thing. Let me add few more points over here. Let me add 11 and let's go for 13. Okay, now we okay. Now we have 10 and now should we have 12 over here or not? Is 12 over here correct?
no, because
Okay,
the
then what should it be?
root is greater than the no leaf. No,
Yeah, root is always going to be greater than the left subtree, but we are going to follow this traversal now. So it's left subtree, then root, and then right subtree. So when we are at this particular right subtree now, this is a right subtree, it's a tree in its own, right? So because it's a tree on its own, it's also going to follow the same order,
Yeah.
which is left subtree, root,
Root
and
and
then
right.
right subtree. So it's going to be 11, 12, 13. Okay, what's next? Anybody just
15
open up
and
your mic?
16.
15,
15
16,
and then 16, perfect. What's next?
17.
17. 17.
17, perfect.
55.
55,
71. 90 and 100.
71, and
90, 100.
90 and
90
100.
and 100. Perfect. Okay, and let me just let me just ask you this. If I would have had 80 over here, where
And it
should I
would be
put 80?
71, 80, 90, 100.
Perfect. It should be 71, 80, 90, and 100. Perfect. This is called in order traversal. Okay. Perfect, guys. Let's talk about pre-order traversal. Pre-order traversal. And the rule over here is that left subtree, then right subtree, if I'm not wrong. Just check. Pre-order, it's okay. It's root first. It's root, then left subtree, then right subtree. Okay. So what should be the order this time? Guys, open up your mics and speak up. Again, we
70,
just have to follow the same.
17,
Perfect. Perfect.
15,
17,
71,
15,
15.
71.
71.
Okay. We are at 15. Uh, okay. Root. Okay. So you are saying that it should be 17, 15, and 71,
Yes.
right? But now think about it and correct me if I'm wrong. But 17, 15, it's correct. Okay. So we are at 15 now, right? We are at 15 over here. We are at this particular left subtree. Now, this left subtree has to follow this traversal as well, right? So it's root, then the left subtree, right? Which is this, and then the right subtree, and then you're going to jump towards the bigger right subtree. What do you think about this approach?
Yeah, it's meaningful. It's correct.
Yeah. So the thing is that this is so always remember that whenever you are going towards one side, it's going to be whenever you're going towards one side, it's you know you're going to encounter another binary search tree. Okay. You're going to just encounter another tree, and it's you just have to follow the same steps and the same ordering in that as well. So given that you are here, when you come towards the left subtree, this is the left subtree, right? But that doesn't mean that you won't follow the same ordering that you were following over here. So after 15, it shouldn't be 71 because we have an entire tree to traverse over there, right? So you just have to follow the same one. Just forget about this entire left subtree and just this entire binary search tree and just focus on the left subtree at the moment. So it's going to be okay. So now, given all this knowledge, now tell me what should be the traversal.
15 to 10,
15 to 10, perfect.
10 to 6,
10 to 6, okay.
to 1,
1, perfect.
10 to 12,
10 to 12,
11,
11,
13,
13,
13, perfect. Next,
16, 16,
16, next,
71.
71, perfect. Now we are at this right subtree. And now we can perform the traversal. 71,
55,
55,
90,
90.
80, and 100.
This is the pre-order traversal. Okay, I hope that pre-order traversal is clear to all you guys.
It's like starting from the root, then going to the left side, then
Yeah,
exploring all the nodes
absolutely,
of
absolutely.
left side, like we do in DFS.
Uh, that's different from DFS because like
We
we are following
explore.
a certain rule.
Yes, no, I am just
Like
relating it
yeah,
so that I
yeah,
can
yeah. You can
have
give
some
this analogy.
intuitive
Yeah.
idea.
Yeah, you can actually take this analogy because you are just taking towards the left subtree at this moment, right? Just going towards
Mhm.
left, left, and left and left. This can be an analogy,
And
but
then
don't
exploring.
confuse.
Mhm.
Yeah, but just don't confuse yourself with this.
Yes,
Like
yes, yes. I'm just
yeah,
relating it.
yeah, yeah, yeah. It's always good to relate. Okay, so let's talk about pre-order traversal. Okay,
I
so
think
in
we already
pre-order
discussed
traversal,
it, right?
oh yeah, talk about post-order. Post-order traversal. And this time the ordering is going to be left subtree, then right subtree, and then root comes at the last, very last. Okay. So root isn't getting the same treatment it was getting before. So root is going to come at the very last. And now tell me what's going to be the post-order traversal. This is a tree in front of you. and I'll be jotting them down. Let me just zoom it out a bit. Yeah, tell me, guys, what should be the ordering of this?
1.
It should be one. Perfect.
Uh, 11.
Okay, 11. Why do you think it's 11?
It would be 6.
Because
Because
yeah,
6 is a
absolutely.
root. 6 is a
Yeah,
root.
6 is the rule. Okay,
Yeah.
okay. Now let me just clarify this bit for you. So you thought that okay, so we are at this juncture, we are at over this uh, binary search tree. So we don't have a right step tree. So let's just jump to this right step tree, right? That's what you might have thought.
Yeah.
But remember that remember that every right step tree or left step tree is a tree in its own,
Yeah.
right?
Yeah. Yeah.
This is going to be isolated from this. Okay.
Yeah. True. True.
So it doesn't when it doesn't have a right step tree, so you just have to ignore it. It's not like that it's going to borrow 11 from this one because it doesn't have a right step tree. It's an independent tree on its own. A mini tree, that's for sure, but it's a independent tree on its own. Right. So the traversal is going to be now tell me what's going to be the traversal.
1, 6.
1, 6, good.
12.
Are you sure it's going to be 12?
1, 6, 11.
Absolutely, it's going to be 11. And let's
13.
clarify why it's going to be 11. Just give me a second. Let me just clarify why it's going to be 11. Because when you're done with this now, when you're done with this tree, you when you're done with this, you are going to jump to this tree once again, right? And now you're going to jump towards the right step tree, which is this one, right? And you might think that okay, so now we can perform like we can actually give 12. So that's not true because over here you have to perform the same ordering once again. It's going to be 11, then 13, then 12. Okay. So yeah, please continue.
Then 10.
11,
11.
and
13. 13. 12.
13, 12, perfect.
10.
10,
16.
16,
15.
15,
55,
71. 71. Oh, 55.
55. Perfect.
80,
Next,
190,
80, 100,
90,
90,
71,
71. Perfect. And at
and the
last,
root.
70. This is going to be the pre-order transfer. Sorry, post-order transfer. Sorry. So in the post-order traversal, you're going to get the the root of the entire tree at the very end. Okay. So these were the traversals in binary search trees. Okay. Does anybody have any doubts regarding this? Anybody having any doubts? Or we should move on to some other interesting topics that are waiting us. Okay, one more thing. Can anybody tell me how can I get the maximum and the minimum elements of this entire binary search tree?
The rightmost element will be maximum, and the leftmost element from the root node will be minimum.
Absolutely. So just wait a second. Just give me. Okay. So as you said, that the rightmost element is the least element, and the the leftmost element is the least element, and the rightmost element is the largest element. So that's pretty, understood regarding this. Okay, let me check if we have something left. Okay, we just have two more, concepts to study about PSC, and then we'll be jumping to aviary trees. So first is insertion in PSC. Okay, and insertion in PSC is pretty simple. So let's take a pretty small PSC this time. Five, six, three, two. Let's keep it 15. Okay. Now let's say I want to insert let's say uh we have to insert 4. Okay, so the process of inserting 4, it's pretty simple. Just go to the very beginning, which is the root. Okay, and then just travel down the line. Okay, just travel down the line. So it's going to be like it's 5, so 4 is less than 5, so we are going towards the left, just like we do in binary search, right? Just go towards the left. Okay, then we compare it with this particular root, which is 3, and 3 and 4 is greater than 3, so we have a space over here, so we are going to put it over here. This is just basic insertion on SGs, right? uh, this is one thing.
How do we insert any number in a heap?
In a heap, when you have to insert, okay, so it's pretty simple how we have to insert an element in a heap. So we just have to add that element at the very bottom, and then swap it. If there is a conflict, then just swap it with its parent.
Okay. So in a heap we swap it, but in a binary search tree we don't swap.
There is no, there is no sense in swapping it, right? Because like
Okay.
if I just add 4, let's say if there was an element, and now I have to uh, you know or let's say I want to add another element which is 5.5. Let's just take it 5.5. So I just add it over here, and though it's correct, okay, wait, I like in BSC you can't perform that now. You can't perform that swaps because in heaps you have a structure like
Hmm.
in heaps you don't have any holes like this. So this is a hole, right? We don't have any element over here.
Okay.
So in heaps you don't have this hole. Whereas in binary search you're going to have these holes. So that might create a problem. So we won't be swapping elements over here. You're going to travel down the tree just like you do in binary search tree, and then you're going to find the ideal location. I think that answers the question. Hello.
Yes, yes. Thank you.
Okay. Okay. That's insertion. Let me check how. Okay. So for deletion. Okay. Let's check for deletion as well. Let's say I want to delete 6, or let's say I want to delete 3. Okay. I want to delete 3 now. How it would be done? Because it's not a leaf node, because like, if it would have been a leaf node, let's say delete 15, then we could have just simply removed it, right? There is no point in having any troubles with that. We can just simply remove 15, but over here it's not the case. It's not a leaf node. So what I want to do is just simply remove it and replace it with any one of the children, and the binary search tree is going to be maintained, right? The binary search tree is going to be maintained. You can replace it with any child. It can be the left child or the right child. That's up to you. That's how you delete it in a binary search tree. Okay, I hope that's clear.
Yeah.
Perfect. So move on to uh, let's move on to avian trees, and we'll be talking about avian trees in a large context now because we have much to discuss about avian trees. So let's talk about. At this point, we are just not even looking at the questions that I've planned, but just going ahead with each and every topic for discussions. I hope that's not a problem. Uh, let's talk about avian trees. How do you guys want me to just discuss the questions? Hello?
You
Uh,
can give a basic intro
I,
about AVL.
Okay.
yeah,
And
let's
then we can discuss a question.
Yes,
yeah, let's
as
go
it is
topic
one of
based.
the important topics.
Okay. So now let's talk about avial trees. Now, what do you understand by avial trees? Like they, before understanding about avial trees, we have to understand about a basic concept, which is one of the concepts, or not a basic, one of the concepts of avial trees, which is balancing factor. Balancing factor. And balancing factor basically means that height of left minus or left subtree minus height of right subtree. Okay, this is what we have. This is what balancing factor means. And given a binary search tree, say 5, 15, 10, 11, 4, 71, 60, 90, 80. Okay. So over here, the balancing factor. So how are you going to calculate the heights? So first of all, let's talk about the height of this tree. The height of this tree is the number of edges, the maximum number of edges it takes you to get down to the leaf node. Okay, the maximum number of edges. So in this case, it's going to be
3.
this, going to be this, this, and this. This is 3 in this case, right? The height of this tree is going to be 3. Now, what do I mean by height of LST minus height of RST? We're just going to calculate the height of this left subtree, and then you're going to calculate the height of this right subtree. And that's going to give you the balancing factor. So, can anybody tell me the height of the right subtree? Right subtree.
It's
What's the height of the right?
3 and
Huh?
it's 3.
The height of the right subtree, are you sure? This right subtree.
Uh, Sub tree, no?
Huh?
Yes, sub tree is 3.
Sir,
I
minus
had
1.
one doubt, like, uh, I had one doubt here that
Mm-hmm.
when we say level, then we start
Mm-hmm.
with 0, and when we say height, then we start with 1.
When we say what? Can you please repeat?
Level. Like 71 is
Mm-hmm.
on which level, and
Mm-hmm.
if we ask 71 is at which height, difference between level and height.
Difference between level and height, it's just like uh, this is level 1, level 2, level 3, right? And like height is just levels that you have. Okay, so like if I take a tree, let's say this is a tree with just one node, this have a height of 0. It doesn't have any height. But if I add a node, and this is level 0, right? Level 0 as well, or you can take level 1. That's just the common notation, whichever you want to follow. And this have a height 3, and this is level 1 and it have a height of 1. So level and height, like thing that you can take it, you can consider it like height of an entire tree is one thing, but when you're considering, so where is 10? So which level is 10 at? So it's at level 1 or level 2, whatever you want to denote it with. So I usually start with level 0, so it's level 1 over here. Okay. So like levels, you can like level can be used to define where a particular element is, and height is for the entire tree. That way you can understand. Okay. So what should be the height of this right subtree, guys?
2.
2.
2. The height of this right subtree is 2. What is the height of the left subtree?
1.
1. Right. And the balancing factor comes out to be -1. Okay. So this is how you are going to calculate a balancing factor. That's one thing. Okay. Now, what does an avial tree mean? It's the simple definition of an avial tree is that any binary search tree with a balancing factor of -1, 0, or 1 is avial tree. Is an avial tree. It's an avial tree. Okay. So let's check. Uh, okay. So that's an avial tree, which the if in an avial tree, if a binary search tree have a balancing factor of -1, 0, and 1 at every level. Now here is the difference coming out. At every level, then it's an avial tree. Now what do I mean by any every level? Let's just check this tree once again. Okay. So this is level 0, and we can see that the balance can. Okay, so let me just redraw this tree once again. 15, 15, 10, 71, or just take whatever we have at hand. 9, 11, 60, 80, 90. Okay. So the balancing factor of this entire tree, the balancing factor of this entire tree is going to be 2 minus 3, which is going to be -1. Okay. The balancing factor of this left subtree, we have to calculate for each and every subtree. Okay. The balancing factor of this subtree is going to be 1 minus 1 is 0. It's also viable, it's also good. The balancing factor of this one, it's going to be 1 minus 2, which is -1. So if in a binary search tree at every level or at every subtree, it may it be right or left. So if at every subtree the balancing factor is 0, -1, or 1, it's an evil tree. Okay, it's an evil tree. So that's how that's how that's the definition of an evil tree. Okay, so I hope that this evil tree definition is understood by you. Should I explain this once again?
Understood.
Perfect, understood. Now I am going to discuss a really interesting topic with you guys. Okay, a really interesting topic that I'm going to discuss with you is is the number of nodes required for an avial tree of height h. Okay. Do anybody know about this formula? Like, what's the formula of this? Can anybody tell me? What's the formula for this? Like, there is a formula given in our lectures, right? What's the formula?
2 to the power h plus 1, 2 to the power h plus 1, minus 1.
Okay. So, okay. So the formula is what you said, 2 to the power of h
2 to the power h plus 1, h plus 1,
h plus
then
1. Okay.
minus 1.
Minus. Okay. I am not sure about this formula, but the formula which I have known from the lectures was that the height of the number of nodes required to the number of nodes required for an avial tree of height h is equal to the number of rods required in an avial tree of height h minus 1 plus number of nodes h minus 2 plus 1. Okay, this was the formula that's been given in our lectures. Okay,
Yes, yes. I guess I am getting confused between BST and avial tree. That
yeah,
formula is for BST
yeah,
or
yeah,
heap.
yeah. Yeah. So basically, this formula is for the number of nodes in a BST, in a complete BST. Most probably that's the case. But this is the formula that's been given to you. But I'm not sure that if we have been given a proper explanation from where this formula has been derived, and that's what I'm going to give you. That's what I'm going to give you. Okay. So let me just explain the derivation of this interesting formula, and at the end of it, you will be able to understand. So, okay, so this was the reason that this formula was derived from. Okay. So tell me, to get an avial tree of height 1, how should the avial tree of height 1 look like? Can anybody tell me? Can anybody tell me how an avial tree of height 1 can be? Like, there is for sure there's going to be a root, right? There's
Root,
going to be a
then
root,
two leaf nodes, then two leaf nodes.
two leaf nodes, okay, but this makes the balancing factor 0. We are talking about minimum. Okay, so okay, I haven't added this clause over here, which is minimum number of nodes required. Okay, so when we are considering minimum number of nodes, so having a balancing factor of, so this BST have a balancing factor of 0, right? Can I? Is this the minimum is this the minimum aerial tree for height h1? Can anybody tell me?
Uh, we can remove the right node.
Yes.
Absolutely, we can remove the right one. And now the balancing factor becomes 1 minus 0, just 1 right now. So this is the minimum that we have. Okay, perfect. What's the how will the uh, minimum aerial tree of height 2 look like? Can you tell me? Like, it's going to be something like this, right? It should be like this, and it should be like this. It should be something like this, right? Am I right? This is the avial tree.
Yes.
Yes.
Like, we can see that the overall BF or balancing factor is 1, is 1, 2, 3, and minus 1, which is 1. And okay, so this is a leaf, so we won't calculate it. So for this subtree, the BF is 1 minus 0, which is 1, right? So we are we are getting a balance. We are getting a avial tree over here. Okay, this is the avial tree for height. This is a minimum avial tree for height h2. Now, just think about it. For an avial tree of height 3, we are going to create a root node. Now, how about taking the this entire tree, because we know that this is an avial tree of this is the minimum tree of height h2. How about taking this entire tree and placing it over here on the left side and taking this h equal to 1 and placing it over here? Is it making any sense? Like, is this viable? Is this possible? Or am I making a mistake over there? What do you guys think? This is here, this is here. Look, we already knew that this is the h, is the height 1, minimum avial tree. And this is h, this is the avial tree, this is the minimum avial tree for height 2. When we have to create an avial tree for height 3, why not just add a root at the top and increase the height by 1? Right? You can see the height of this avial tree is 3, right? And what we did was we just simply used what we already had. We simply use the minimum, we simply use the avial tree of height is equal to h2, uh, h is equal to 2, and h is equal to 1. We already know. Okay, so what we have to do now? What we have to do now? We just have to calculate the BF. Okay, so the BF of this entire tree becomes 1, 2, 3, 1, 2. This is 1. Now, as we already know that we also have to check the balancing factors of the left subtree and the right subtrees as well. Right? We already know that for this left subtree, the balancing factor is 1 and it's an valid avial tree. And the balancing factor of this right as well is 1 and it's a valid avial tree as well. So rather than thinking of a tree which is, h is equal to 3, we have to think about it. Rather than thinking about it, we just use this. We just use what we already had. And in the similar fashion, in the exact similar fashion, can anybody tell me how am I going to get an avial tree of h is equal to 4?
Same we have to do on left side h minus 1 and on right side h minus
H minus
Means
2.
on
Perfect.
side of h3.
Left side, we are going to add h3. Okay. And on the right side, we are going to add h2.
two. Yeah.
This is the minimum avial tree, minimum node containing avial tree for height is equal to h square. Right. And now, are you getting an intuition about the formula? Why the formula is n is equal n minus n h minus 1 and n h minus 2? Because the number of nodes in h is equal to 4, it's basically number of nodes, which is n is equal to 3, number of nodes n is equal to 2 plus 1, which is the root. That's why the 1 comes over here. That's the reason there is a plus 1 over here for the root. Are you guys able to understand like how you know how
Yes.
beautiful and simple this derivation of this formula was? Like when I was a
Yes.
student of PDSA, I used to I just mugged up this formula. What this formula is, I just have to mug it up. And the minimum number is like it's h minus 1, h minus 2 plus 1. That's it. Now, and very recently in the past term when I was teaching it to another student, during a private tuition classes, I just realized this is the reason why we are having this particular formula. Then it clicked to me, okay, so this is just, you're reusing the previous AVL trees that we already generated. So that's how this is going to work. Okay, and this is how the formula is derivated. So whenever you are given a question, just remember, so okay, so this is the intuition behind it. And if you have to draw the, you just forget this formula, just draw it out. You're going to get to the answer, right? So I hope that this part is clear to you, all of you. Right? This part clear to all of you?
Yes,
Yes.
it's clear.
Perfect. So given that we have solved this, so let's look at the question at hand as well. So consider the following AVL tree. Which of the following is resultant AVL tree after inserting a new element one in the given AVL tree? Okay. So all right. So this question is regarding rotation. So we have to look at rotations as well. And rotation is just another interesting part of AVL trees. By the way, AVL tree is one of my favorite topics in this entire. So it is so interesting to just follow along with trees and look at how they're behaving. Okay, let's talk about rotations. Oh, we're just spelling the rotations. Okay, so we are going to have, so in rotations we are having two different kinds of rotations. The first kind is single rotations and double rotations. Okay, single rotation, double rotation. So we'll be quickly going through all of them. So in single rotation, let's talk about single rotations first. Single rotations, and over here we have two different kinds once again. So it is firstly rotations. It is L rotation and RR rotation. Okay, L rotation, RR rotations, and let's talk about.
Mr. Sunny,
Oh yeah,
sir, can you ask Mr. Shitich just to send the link for the syllabus again? It's not opening the link for the drive.
Kshitij, are you
Hello.
there? Hello.
And thank you for
Yes.
the last time for the quiz one. 80% paper come from your revision. It's very nice.
Thank you. That's right.
Yeah, hope and you will be taking for the Java also, right?
Oh no, I won't be taking Java.
No, like your house will be taking for the Java also, right? Like last time.
Most
Last
probably,
time,
I'm not sure about that.
last time we had Java. This time we don't have session for Java.
Please take, sir, tomorrow if possible. Please take. You guys helps a lot of people working professional, especially seriously. 80% marks come from, especially the weight section is very nice. Sorry for wasting them. I will just keep on following. Just
No
please, if
worries, no
possible,
worries.
pick Java.
I'll discuss it with the secretary,
Yeah, please,
and
please, please.
I'll just let you know. Okay.
Yeah, please, sir. Thank you so much. And please continue. And just ask
Yeah,
Mr.
sure.
Sitish to send the link again, please.
Regarding the syllabus, na,
Yeah. That note syllabus, yes.
regarding the syllabus of quiz 2, right?
Yeah, it has notes also, right? I think in that link.
No, its
Okay, that
notes
I'm
is
not
there.
sure
It's
about.
opening now.
Yes, sir. Hello.
Yes.
It has notes also, right?
Yeah,
Are
it
you
has notes also.
are you in any yes, are you in any WhatsApp group?
Yeah, in WhatsApp group. Yes.
Okay, so I will send you that.
Yeah, I'll send hi now in the PDSA Ace group. I'm sending
Okay.
hi now.
Yes.
I just sent hi now over there. And thank you so much.
Okay, guys. So let's just get back to it and quickly complete all these topics. So next we have left rotations. So what do we understand by left rotation? So firstly, let's understand why do we actually need rotations, right? So these avial trees, they have a problem, right? And the problem is that sometimes they are not avial itself. Okay, sometimes they can be crooked, they can look weird and all. And let's say, can you call this an avial tree?
No.
Why?
Not
Balancing
the
factor.
balance factor is not one.
Balance of is tree, right? So we can't call it an avial tree. So this is now how you can actually do some operations to create it and to actually convert it to a avial tree. And sometimes why do we have to do this rotation is that let's say that you had an avial tree which was a pretty well to do avial tree on its own. It's an avial tree, let's say. And given this avial tree, let's say somehow, and because avial trees are binary search trees itself, and let's say you had to insert an element over here. Now you will see that this is not an avial tree anymore. Just inserting one element just took away the status of avial tree from it, and it's just a poor old binary search tree, right? How we can fix it? How we can actually make it into an avial tree once again? So we are so the solution is rotations. Okay. In the rotations, we have single rotations and double rotations. And in single rotations, first we will be looking at single rotations, and we have in single rotations we have two different types of rotations, which are left and right. Sorry, left and right. So in left rotations, let me just draw the graph for you. Let's say this is the avial tree. Okay, this is the avial tree, and we have to perform left rotations. Now, what do we understand by left rotations? It is that that uh, okay, just look at it. This particular part of the avial tree is the main reason for our problems, right? This part was not like this part is creating a problem for us because you can see that this is a perfect avial tree, or is it not? No, no, this is not a perfect avial tree. So this is not a perfect avial tree. This have a balancing factor of 2, right? So we can see that this is the infected or the troublesome region of our avial tree, and hence we have to perform left rotations, which is like we have like the nodes are in this particular format of left and left, right? We have left rotation. So while doing a left rotation, the now I'm going to do some color play just to make you understand what's going on. This is green node. Let's say this is the purple node. This is the yellow node. Okay, here it goes. The rotation is going to look something like this. Uh, the purple node will become the root node now. Okay, just be aware of the color coding that I have done. It's going to become this one. Here is the yellow node. Then wait. It's going to be that will be right. check. Okay, I'm not doing it right. Okay, so it's going to be the green node is actually going to become the root. The purple node will be the
I think
purple
so.
node will be here.
You were right before.
I was right before. Okay, okay, okay. Let me just go along with this and check if I will get to a possible solution. Wait. Uh, is this a right event? Is this a valid event tree, guys?
Yeah.
No.
Wait, just let me check it. If I remove this particular part, then green is going to climb up. Okay. And it's going to be, yeah, this is right, I guess. Like the balancing factor over here, the balancing factor of this tree is going to be 0. This is going to be 1. This is going to be -1. It's a valid tree, right? Yes, just confirm that. Can anybody confirm that if this is a valid tree?
Yeah, it is valid.
It is valid, huh? Yeah. So this is how the rotation is going to happen, and this is how the color coding is going to be. So if we just color code these as well, the red code will come over here. Okay, this is how the rotation is going to happen. Next comes the right rotation, right rotation, right right rotation, and let's just take a mirror image of that. Let's take it like this. Okay, this is the evil tree that we have at hand. Okay, so because we can see that the shift is towards the right, so it's going to perform it's going to be a right-hand rotation. Okay, and the result is going to be, again, we are going to color code every one of them. Green node, this is our purple node, this is our yellow node, and okay, so let's take it like this is our red node. It's going to become something like this. Something like this, right? This is just a right-hand rotation. That's how it's going to be. I hope there is some doubts over here. Any doubts regarding this? Okay, I hope there are not. All right, so let's move ahead with double rotations and let's be done with avial trees. Double rotations. First one is LR rotation. What does LR rotation mean? Let me just draw a plot for you. Is this the validated trick? Tell me this. No, right? Because the balancing factor is 2 over here. So the the point of problem, the point of problem is this, right? The point of problem is this, and we can see that it goes towards the left and then it goes towards the right. The point of problem is over here, right? Because of this, we are having a 3 on the left subtree and sorry, we are having a 2 on the left subtree and a 0 on the right side. Is it? Yeah, on the right side. So this is the point of mistake that we are going to, that we are making. So it and the formation of this tree is it goes left and then it goes right. Right. So we are going to perform LR rotation of this. And how does this rotation actually play? So basically, this is LR, right? Because it's going left and then it's going right. We are going to convert it to something we already know. And this is the beauty of of DSA, that you know something and you have a new problem to solve. You convert that new problem to the problem you already know. Okay, so we are going to convert this LR problem to LL problem, and then we are going to solve it. Okay, and how we are going to do that? Again, I'm going to color code stuff. So it's going to be let's just color code this with the green node. This is the red node. Let's just take purple. This is the purple node. This is the yellow node. Okay. Now for LR rotation, just bear with me. It's going to look something like this. The green node will come over here. The yellow node will be over here. The purple node will go to this side and the blue node is as it is. Okay. Now, is this looking something similar to you? Is this looking something similar to? Is this looking like an L rotation kind of problem, which you already did, right? This is the problem which you already did, LL rotations. This is exactly the problem we created, LL rotations. So the solution would be it's okay. It's going to be, let me mark this as an orange node. This is the orange node. Okay. The structure it's going to get into is green node will rise as the root node. Purple node, purple node is going to go over here, and blue node is going to follow it. Then orange node will become a child, and the normal blue node is going to be over here. Okay. Where now? I want you guys to tell me where should the yellow node go? Should it go over
Opposite.
here?
No, opposite
Child
side.
of orange.
Exactly, it should be the child of orange because we know that the yellow node is definitely greater than the green node, right? Again, we are doing BST, binary search tree. It's greater than the green node. So one might think, okay, so if green node is going up, so this yellow node can go over here to purple, but that's not possible, right? It's
Yeah,
not
purple
possible
is
because
less than green.
purple is less than green. If you attach yellow over here. That won't make sense. That will just break the binary search tree, right? So this is how the LR rotation is going to take place. Now let's come to L. Huh? Yeah. Please ask the question.
So in which case we have to perform LR, and in which case we have to perform RL or LL.
And this question will be asked when we are going to answer that question that we just saw. That question from the PYQ. So just bear with me. We are going to answer that question, and you will know that which rotation we have to perform. Okay. So let's talk about RL rotation. And now this time you guys are going to tell me where which node is going to go. Okay. This time the tree will look something like the mirror image. Okay. Okay. Orange. Orange node at top. Uh, then we have a purple node. Then we have a green node. Okay, wait. Okay, green node over here, and yellow node following it, and here comes the blue nodes. Okay, this is the tree that we have. Again, it's not a naive tree because the balancing factor is 2. Because the balancing factor is true, so we have to perform rotations. And this time the problem lies in this, right? The problem lies over here. And the structure is first it goes right, then it goes left, right, right, and then left. Okay. So we are going to convert RL problem to first RR and then we are going to solve it. Okay. Simple as that. So let's go ahead. And now this time you guys are going to tell me what's going to happen. Tell me guys. What should I? How should I convert it to RR rotation? Now tell me where should all these orange, purple, green, and yellow nodes go? Anyone? Okay. Let me just answer this particular part. So it's going to be the green node will be over here. It will push the purple node over here. The blue node will be over here. And the yellow node will stick onto the left child. And here it goes. Okay. Is this right? Or is there a flaw?
Correct.
Correct. Huh? Now tell me how you're going to solve it. Because now it has become an RR rotation problem. What should be the answer this time? Tell me. Let's start with the root. Which node should become the root?
Green.
Exactly. Actually, the green node that should become the root. What should be the left child this time?
Orange.
Orange is the left child. Perfect. Then we have this.
At the
Now
right, we
the
will have purple and then blue.
purple and we have blue. Where should the yellow node go? Should it go over here or should it go over here or should it go here, here, here? Where? Still, where should the yellow node go? Anyone? Just make a guess. Nobody's
Purple.
judging you over here.
Right side of orange.
Right side of orange. Anyone's said purple as well, right? But let me just tell you why it won't be purple. Because yellow node is great
less
is
than.
less than the green node, and it's less than the purple node. Okay. So it's less than the green node and less than the purple node as well. Now, if I attach it over here, it satisfies one condition, which is less than the purple node, but it doesn't satisfy the less than the green node node, right? And that's where it won't make the cut. Okay, these are the rotations that we have to follow. Now finally let's just look at the question that we had, and the question says that this is the AVL tree, and okay, given they're inserting a new element. Okay, so first of all, this is a question for all of you. This is a BST, like the AVL trees are BSTs. Tell me, where would the element one be inserted?
Like 20 left side.
20 left side. You were saying that we should add one over here.
Left side of 3.
Exactly. It should be left side of three. Why it won't be over here? Because obviously, like, yeah, just look at it now. If one is going to be here, it should be greater than 10 as well.
Ah,
That's
okay.
not the case. Yeah. So one is over here. Okay. Now, is this a valid AVL tree?
No.
It's not a valid AVL tree because the balance factor is, what's the
2.
balance factor?
2.
Exactly. It's 2 because the height of the right tree, sorry, left tree is 2, whereas the height of the right tree is 0. Right. So it's 2. Hence, it's not a valid AVL tree. Let me just draw it. Okay. It's not a valid AVL tree because the valence factor is, it's jumbled up. Now tell me what you're going to perform. You have to perform rotation, right, to rectify it. What should be that? Like
So
we
it's
know. So first of all, the I'm sorry for cutting you. So first of all, you should identify the region of problem, which is this, right? This is creating the problem. It's very long and it's creating the problem. Now you can clearly see which rotation we are going to perform. First of all, tell
L
me which rotation we are going to.
L.
LL.
Exactly, we are going to perform L rotations. Because once you identify the region of problem, now you can get which rotation you have to perform. So it's LL, right? And it's going to be, now tell me the rotated form. Tell me the rotated form, what it should be. LL rotation. Now here we don't have the color coded nodes. So maybe you will be struggling over here, but just think about it. In LL rotations, we're going to shift from this side to this. Right. Just think about it. What should be LL rotation? So
5
5 will
voltage would be a root,
5 will be the root. Perfect. What else?
and 3 to the left,
3 to the left. Perfect.
1 to the left,
1 to the left. Hmm.
and 10 to the right,
10 to the right. Perfect.
8 to the left of 10,
Perfect. This is the rotation that you perform, and just select the tree wherever it is. It's over here. Option B. Okay. So this is how AVL trees are going to be performed. Okay. So this this is where week 7 ends, and the next comes divide and conquer algorithm. And so This is where the divide and conquer algorithms comes in week 8. But let's see that if I don't think that we will be able to cover that in this session. It's already past 12, and we have to wrap up the session. But before wrapping up, let's if you guys have any doubts, you can kindly ask me if you guys have any doubts, because unfortunately we have to end the session over here because of time limits. So any questions that you might have regarding anything that we talked? Any questions? Any doubts you might have had regarding any other topic that we haven't even discussed?
Divide and rule. Can you give us a brief?
Okay, I'll just give a brief intro about Divide and Conquer. So, have you heard about this term, divide and conquer, anywhere before?
Yes, in history, like the partition of India.
Yeah, and also you might have heard this term, during the British Raj, whatever, how they,
Yes,
divided uh, the
India.
subcontinent and, conquered uh, princely states like Jhansi and all. So, uh, this is the exact same technique that we are going to perform in PDSA. So it's just history is just repeating itself, and we are going to use this technique uh, in data structures and all those. So we have divide and conquer. So I'll just give you a brief intro about divide and conquer, and uh, what should we do? Should we discuss insertion and all? Okay, let's do one thing. I'll discuss inversion counting. Inversion counting is divide and conquer technique, and I'll be discussing that. So while discussing that, we will be able to understand what is divide and conquer. Report 69, 12, 1. Okay. So this is an array given to us, and we have to find how many inversion pairs are there. Now, what does an inversion pair mean? Inversion pair means that given a sorted array, let's say this is the sorted version of this array, right? It's the sorted version of this array. Inversion means that how, like, how should I explain? So if you just draw the lines between the place it should be and the place it is, like this, the number of intersections in these lines is going to give you the inversion pairs. This is a technique that you can do if you are short of time. You can do this. You can just do this technique. Just put uh, you know, the sorted list below it and just draw the lines. Just match them out, and the number of intersections that you might have. Let's say that this is an intersection. This is an intersection. 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 So these are all the intersections. So this is a way. It's a shortcut way to do it. But usually, what we do is we apply divide and conquer, and that's the very reason we are looking at this problem as well. So we're going to perform divide and conquer on that to get the inversion pairs. Okay. And how do you perform divide and conquer? We'll be performing which is called something called merge sort. Okay, merge sort. We'll be performing merge sort. And the technique is that you will partition, just like Britishers partitioned our country. We are going to partition this entire array into two. Okay, we are going to divide this array into two, which is going to give us two separate arrays. Okay, then we are going to partition this array once again. Partition. Okay, yeah, partition it once again. 71, 8, 54, and partition this array as well. 69, 12, 1. Okay. Then partition this as well. We want singular numbers. Partition this. So now we have got singular numbers. Okay, now we have singular numbers. Now, okay, let's remove this because this was already partitioned in the previous stage. Now, what you have to do is after doing this, after dividing them, you have to merge them. Okay, now what does merging mean? Merging basically means that it actually follows a rule, and the rule says that, okay, so let's say that this array is A and this array is B. The rule says that if is greater than, I hope you understand this terminology. A, the first element of array A and the first element of array B. If this is the case, then count inversion, count inversion, and put first. Okay, put B, the first element of B first. So when we are going to merge these two arrays, it's going to be 8. 8 is going to come over here, and then it's going to be 71. This is a merged array. Okay. Next, we are going to go towards this side. We also see, okay, so also we will be counting the inversions over here as well. So the inversions are going to be uh, inversion count, inversion count, and I'll be doing tally marks because we are counting them. Okay, so this is one inversion because the first element of A was greater than the first element of B, so it's one inversion. Next, we are at this one. So it's so again the first element of A is greater than the first element of B. So that's 2. We're going to merge them. 69 over here. Okay. Next, after this, we are going to merge 871 with 54. Just like so, this is the dividing step. This is where you are just going to divide stuff, right? This is where you're going to divide, just divide them. Divide them, dividing till single numbers, and now you're going to merge it back to the entire array. This is the merging step.
Excuse me, sir. Why are we doing that?
This is required to actually count the inversion counts.
Got it, sir.
Yeah, and divide and conquer is a technique which is used in merge sort. So merge sort actually uses divide and conquer, and yeah, merge sort uses it, quick sort uses it, and quick sort does it use it? I'm not sure about that. Merge sort it definitely uses this particular method of divide and conquer. So we're just going to perform merge sort on this, and we are going to get the answer of inversion counts. Okay, so here comes 12, 69, and we are going to merge it with 1. And this time, the A, and this is the B array. Okay, so again we are going to check. So is the first element of A is greater than the first element of B, less than the first element of B. So it is less. So we're simply going to add it in the array. We are not going to count inversion over it because we are going to count inversion only if this is satisfied. This is satisfied. Only if then we are going to only when the first element of A is greater than the first element of B. Okay, so 8 is over here. Strike of 8. Strike it off. It's no longer in this array. And now we have 71 and 54. So now we see that yes, the first element of A is greater than the first element of B. Hence, add another inversion count, and the array would be 54 and 70. Strike both of them. Okay. Next comes inversion of this. Can anybody tell me how the inversion is going to take place? Anyone? Okay. So when we have this, so it's going to be the first element of A and the first element of B. So it's 12 and 1. So 1 is going to come over here and we are going to count inversion. So now we can see that we have two elements over here which have this condition. We have two elements. So one is less than both of these. So we are going to add the number 2 to the inversion count because we are actually the thing is that in inversion counts we are adding, if this is the case, count inversion. So let me just update it. This is the case. The rule is, if this is the case, add length of array A to inversion count. Okay, to inversion count. And so adding it, it becomes 5. And hence it's been striked off. This and then 12 and 69 are going to be like this. And next comes, now I want one of you to tell me how you're going to merge these two. Can you tell me how you're going to merge these two? Anyone? How many people are left in the meeting? We have 10 people. Removing me 9.
The first of B is less than first of A.
Perfect. So you're going to add one
So
over
keep
here.
B first. Yeah.
Huh? And how and what should be the increment in inversion counts?
3.
Absolute. It's going to be 3. Why? Because we are going to add the length of the array 1 of the A array, right? Array A. We have to add that length. So here it comes. This one, and let's check it once again. So the process just repeats once again. Okay. So it's the first element of A and the first element of B because one has been removed. So the first element of B becomes 12. So this time we see that the condition is correct. So it is going to be over here. Strike it off. Okay. Now let's check the first element of A and the first element of B. It's 12 and 54. What should be done?
Again, second element we should add, right? For B.
Yeah, yeah. We are going to add. How many should we add? Should we add in the inversion count? How many counts should I add to the inversion counts?
2.
2.
Absolutely, we're going to add 2 because we have to add the length of the array A. This becomes 10, and adding 12 over here, strike it off. Now it's 54 and 69. So the first element of A is less than the first element of B, and it's nothing but you have to do. Strike it off. Then 69 and
Add
71.
1.
Add 1.
Add 1.
Absolutely. We're going to add 1. And it becomes 69, strike it off, and last is 71. After sorting this using merge sort, we are going to get this, which is the inversion count. This is 11. the number of inversions in this array were 11. I hope this was understood to you guys.
Yes.
Okay. Any doubts?
Is there
Any?
any formula to uh, derive how many inversions we have?
I don't think that there is a formula because like every array is unique, right? So there is no formula regarding that. But there is a short trick which I explained it to you. Uh, the short trick is just just draw the just write down the sorted array and draw the just match them out if and just count the what it's called discount the intersections of those. That's one way to do it. Yeah. Okay, guys. So, uh, okay, guys. So that was the end of it. I hope that you don't have any questions on it. So we can.
Do we have to cover any more topics in the divide and
Yeah.
conquer?
If you have to cover what? Could you please repeat?
Like, apart from this session, do we have to focus on any other topics in the divide and conquer? Apart from the inversion.
Divide and conquer. I would suggest that you should. Let me just check. Uh, I guess there are more stuff. Like there is Karatsuba algorithm, which is this very interesting algorithm. And if we had the time, I would have explained it to you. It's basically that in Karatsuba algorithm, you see integer multiplication done much faster. Okay, so I'll just give an example. Uh, so Karatsuba algorithm, you can just simply study it. You can just search on YouTube, and you will get pretty good amount of videos on that. So given these integers, what do you think is going to be the complexity in multiplying these two? Can anybody tell me? Can anybody tell me what should be the complexity in doing this? And time
What
complexity
we have
concept.
to do?
Huh?
What we have to do here?
You have to do multiplication between. Let- Let's just see it now. Like you have to take first element three, then you have to multiply it with every single digit over here. Then you have to take two, then you have to multiply every single digit over here.
N
So what
square,
could be the
n
time
square.
complexity? N
Yeah.
square.
First, we
Okay.
have to multiply, then we have to add them.
Multiply and then add them. You're talking about Karasuba algorithm, no?
Oh, okay. Okay, fine, fine.
Yeah, I'm just talking about basic multiplication over here. So
Also,
if
add
you
part is constant, so we have to take only n square.
so it's n square, right? Uh, n square is the general way you're going to multiply two integers, right? But Karatsuba, and this n square was actually considered to be, the like someone there was a professor, I don't remember the name, but he claimed that it was impossible to get a time complexity less than n square when you're considering integer multiplication. But during that lecture, there was a student called Karatsuba. He was a Russian mathematician, and what he did was he decided to prove it wrong, and he came up with the Karatsuba algorithm, algo, and this uses divide and conquer. You will get to know how it just it partitions the number into two halves. It takes like 1 to 5 and 6, 7, 8, and then it multiplies stuff with it. So it's very interesting. You just have to just go ahead and check on YouTube and all. So Karatsuba managed to achieve a time complexity of 1.5, and then he shared it with the professor, and he was really delighted, and he he accepted that he was wrong. that it can actually be done in much faster way. So this is the Karatsu algorithm. Just check it out. I am not sure if you will get questions on this, but like you should know about this. Maybe you'll get a statement based question like what's the uh, complexity and all of Karatsu algorithm and what can be done after the division, dividing it one time or something like that. So uh, that's it for the session, and I wish all of you very good luck for the examinations. And I hope you like the session. Hope you learned something from the session.
Yes, we really liked it.
Thank you, thank you, thank you, thank you. Also, I'll share this notebook with the Kaziranga staff, and they will provide it to you using any method. Maybe they will mail it to you or put it under the YouTube video. Don't know about that, but they will provide it to you.
And if possible, you can go ahead with the Java also, brother.
I'm not sure about Java, because
No problem, no problem. If possible for you people. I know
that
you are also all studying only. That's why I'm
yeah,
telling you possible.
yeah.
Thank you so much.
Okay, guys, bye. Thanks a lot. Thanks a lot for joining and thank you for interacting. Bye.
Bye.
Well, thank you all. I'll be closing the session recording and streaming. Thank a lot. I hope the session was useful.
Thanks, Hitesh sir. And thank you for the MLP sir last term. Thank you so much.